Good morning. Here we go, perfect. My name is Lukáš Čamra, and I'm an engineering manager at Meta. I support a team that is responsible for development and innovation of media technologies at Instagram. Today, we will share with you the latest media techniques that you will be able to use in your own apps. And hopefully, you will be also able to take some useful lessons home about how to build a modern media app in 2024. I'm not here alone today. Over the presentation, you will hear from our media experts over a variety of media topics. We represent the Instagram media engineering, and our goal is to make and keep Instagram the leading photo and video app in the social media industry. At the end of the day, Instagram is a photo and video sharing app. Images and videos are literally on every surface and part of every interaction in the Instagram app, and you can probably relate to it. So the media and photos and videos and its performance is extremely critical to the app and to the users. There are several obsessions that define us. First, we are obsessed about media technologies. They are truly the key to enabling new product capabilities and innovation, to reducing cost of running media infrastructure at meta scale, and creating incremental as well as large step changes to the overall media experiences at Instagram and its users. We are also obsessed about providing the best-in-class visual quality. We know that people care about visual quality of videos and photos that they upload to Instagram and to our apps. Our users also tend to engage with our apps more if we are able to serve higher visual quality of media to them. Finally, we are obsessed about performance, reliability, and speed. We know that they are important to our users. Instagram users upload hundreds of millions of photos and videos to Instagram every day, and it is our responsibility to provide the best possible media experience for them with the optimal yet complex technical trade-offs between latency, quality, and cost to meta infrastructure. We support Instagram's products and properties such as Reels, Stories, Direct, as well as recently released Threads app. In today's talks, we will share with you some of our recent media technology experiences that allowed us to bring new capabilities to Instagram and Threads apps, improve their performance, and reduce the cost to infrastructure. Frequently, the impact is far-reaching and, for example, may also reduce users' data costs. We hope that you should be able to apply these techniques and learnings in your own apps. In that way, you will be able to also up-level the experiences to your own users and customers. I'm going to now pass it to Chris, who will speak about photos with HDR capabilities.
Thank you, Lucas. All right, hi, my name's Chris. I'm an iOS engineer on the team, and today I'd like to talk to you about photos. Have you ever noticed that some of the photos within the iOS Photos app seem to glow in a way that happens nowhere else in the OS? These photos are being rendered in high dynamic range, or HDR, and iPhone has been capturing them this way since 2020. In addition to greater brightness, HDR also allows improved contrast and more colors than SDR, and consequently, you get a more realistic image. By the way, this is a simulation because the screen that we're watching on doesn't actually render HDR. Last year with iOS 17, Apple introduced new APIs to allow third-party apps to work with HDR photos too. We took advantage at Instagram, and today I'll be sharing the story of how we went about it, and in case you want to do some of the same, adopt some of the same practices. First, let's dive into what an HDR photo actually is. What is it about these photos that allows the Photos app to see what we cannot? Apple actually has a nice doc about this on their page. I'm going to highlight a few of the key parts of it. The main idea is that there's one part of the photo that you're used to seeing and two parts that you usually don't. Part one is an SDR-based image. This is what you get if you call UI image contents a file that many of us are used to using. It's also what you see if you open the photo in any app that knows how to read a HEIC or JPEG. Part 2 is some metadata. You've probably encountered EXIF data before. Many camera manufacturers use it to encode information such as exposure, shutter speed, whether the flash fired, focal length, etc. But EXIF also has an additional facility called Maker Notes, which allows camera manufacturers to encode additional information. And iPhone camera has been using this to encode 2 parameters used to derive the HDR headroom, which is the brightest white in the image. Part 3, there's a whole other image known as a gain map. It's about half the size of the base image, and it's black and white, and it represents the difference in brightness between the HDR and SDR representations. If you put these 3 parts together, you can reassemble the original HDR image, except you may not have to, because iOS 17 takes care of this for you, and more. Let's take a look. Say we want to make a photo sharing app. First thing we need to do is be able to import images into our app. Our old friend, UI image contents of file, only sees SDR though. We need to adopt one of the new APIs that sees the other 2 parts of the file that we talked about in order to give you back an HDR photo. We've got 3 options. I'll walk through them. UI image reader is the most simple high-level option. Pass it a path to a file and get an HDR image back that you can feed directly to UI image view. But there's one more step. This doesn't quite look as we expected. Remember to set the preferred image dynamic range property on UI image view to high, because the default mode is constrained, which is sort of an in-between that looks like neither the SDR that you'd get if you open your image in any other app, or the HDR that you'd see in your Photos app. So in order to reduce confusion, be sure to set it to high. So far, so good, though. Let's import another image. Uh-oh. Every time we import another image, our memory footprint goes up by about 62 megabytes. It doesn't look like there's a leak, but also it never seems to recover. If we import enough images, the app will crash. Let's try another API. CG image source decode to SDR, or HDR. Get back a CG image, which you have to wrap in UI image, and then you can pass it to UI image view. It's just slightly more verbose than UI image reader, and actually even more so after you add the bridging for the CF types, which I omitted here for brevity. Also be sure to call release if you're using Objective-C. It actually has the same behavior. This time you lose 35 megs per image though. Now we can import nearly twice as many images before the app crashes. Maybe there's a better option though. Let's take a look. Third time's a charm, final API, CI image, expand to HDR. This one gives back a CI image, and it's actually a bit more concise than CG image source. And, surprise, there's no accumulation. However, the image does not quite look as we expect. Unlike with CG image, you can't just wrap an HDR CI image in a UI image to give to UI image view. You need to rasterize it with a CI context first, in other words, create a bitmap out of it, in order for UI image view to display it properly. So much for being more concise. And this has its own catch. Every time you rasterize, we see a huge spike in memory usage, approximately 115 megabytes for this image. This might be too much if we have other things going on in our app at the same time. For example, maybe we're a messaging app too, and we're also processing images coming in from our friends. So if we want, we can reduce the size of the spikes by reducing the size of the bitmap. For example, maybe to half of the original size. After reducing for half, we only have spikes of 45 megabytes each. This will hold us over. There's one more thing we should talk about, though, when talking about rendering HDR in UI image view, and that's reduced headroom. In some cases, the system does not have enough brightness to render the image in full HDR. For example, if you're using low power mode, or if you have certain accessibility features enabled. When this happens, the system will tone map the image to SDR. This process is different from simply importing the image as SDR, and it may be confusing, as again, it looks like an image that you haven't seen in your Photos app before. So, to avoid confusion, you may opt to import only as SDR when low power mode is enabled. So that's importing. Now maybe we want to edit the photos before we upload them. Filters, crops, scales, etc. I'm actually going to fast forward over this step. The implementation of an editing pipeline is pretty complex and outside of the scope of this talk, but it's something you can ask Kevin about later. What we can agree on, though, is that the output of the editing pipeline is ultimately some bitmap image that we need to encode to be uploaded. Ideally, because we'll be sharing the image with people who both can and cannot understand HDR, we'll be encoding it in a backwards compatible format, actually a lot like how the iPhone camera has been encoding us for years with base images and gain maps. iOS doesn't have a public API to do this, though. What iOS can do, despite being able to read gain maps from the system camera, is write a different format called ISO HDR. An ISO HDR is actually a whole HDR image in one piece, rather than three. It's even better than gain maps in terms of preservation of original detail. However, in order to properly handle ISO HDR as the recipient, you have to first know about the format, and then know how to tone map it back to SDR if you don't have a capable display. So what we really want is a gain map. So how do we get a gain map? We have to think like the iPhone camera. The camera captures in HDR, tone maps an SDR representation for backwards compatibility, and then derives the gain map from the difference between the HDR and the SDR. So the next question really is, how do we get a gain map? There actually is an API for this. How do we get a tone map? CI image, tone map, HDR to SDR. However, the output looks the same as it would if you viewed it in low power mode. Different, possibly confusing. We really want to match the SDR output from the system camera. So we need to roll our own tone mapper. And we're lucky to have Haisha, who came up with a tone mapping implementation that looks nearly identical to the output from the system camera. If you don't have a Haisha on your team, you can look up tone mappers on the internet using your favorite search engine to learn more about how to implement one. Now back to this. We have our HDR and our SDR, so we can derive our gain map. How does that happen? Well, remember Apple has that formula in their docs for constructing HDR and SDR given a gain map. As we have HDR and SDR, we can just rewrite the equation to solve for the gain map. Throw it in a CI color kernel, and there you have it, gain map. You may be still wondering about where that third part, the headroom, comes from. Recall it's the brightest point in the image. Here's some code to get that. There's a CI filter called area maximum, which will give you the maximum RGB values in an image. You can rasterize it using our old friend CI context to a luminance bitmap, that's the LF part, and get back a single value, which is the maximum white. So now you know how to make an HDR photo sharing app, and surprise, surprise, this is essentially how Instagram works. Except instead of writing gain maps according to the Apple spec, we're following the Ultra HDR spec. Why? Well, it's directly compatible with Android 14, which also got HDR APIs last year. And we've adopted HDR on Android 2. In fact, if you do all these steps that we just talked about in reverse, you can not only write Ultra HDR on iOS, but read it too. One format for everyone. And that's the story of how we brought HDR photo compatibility to Instagram in a cross-platform, perf-friendly way. And so can you. Now we'll hear some more about images from Kevin. Thanks.
Thank you, Chris. Hey, everybody. My name's Kevin Brewster. I'm an iOS engineer at Instagram, and I'm here today to talk about WebP. First, I'll give an overview about what WebP is and how it works at a technical level. Then I'll discuss some improvements we've made to WebP rendering. And finally, I'll talk about how we are handling WebP with audio at Instagram. So, animated WebPs have a lot of advantages over GIFs. They support full 24-bit color, along with 8-bit alpha, which eliminates banding and ugly borders that you get with GIFs. They can be lossy or lossless, and are 64% smaller on average, but you pay the price in slower decode time. At Instagram, we use WebPs whenever we need proper 8-bit alpha transparency. For example, in the animated avatar stickers that you can add to stories or reels. Or the new cutouts feature, which uses AI to extract the foreground object from an input video to convert it to an animated sticker. Now, let's talk about what a WebP file actually is. As we know, at the binary level, the file is just a sequence of bytes. In WebP, these bytes are grouped into chunks, where each chunk has a 4-byte identifier, a 4-byte size, and a variable-sized payload. The chunk size gives the offset to the next chunk, so you can quickly and efficiently parse a file to find the chunks you are interested in. Now, the first chunk in a WebP file is always the 12-byte header. Next, we have a VP8X chunk that contains various image features, such as the total size of the image and various flags. This chunk also specifies the overall size of the image. Next is the animation chunk, which specifies global animation parameters such as background color and loop count. For example, this may specify that we use a green background or a yellow background, but usually it's clear. Finally, there will be a bunch of animation frame chunks that contain metadata, as well as the encoded frame image data. And this is where we dive into the logic for how to render an animated WebP. We start with the first frame. The frame X, Y, width, and height specify the rectangular area that this frame will draw to. The frame image data contains the VP8 encoded image at the specified size. We decode the image and draw it onto the given rectangle. We wait for as many seconds are defined in the frame duration, and then we move on to the next frame. Before moving on, though, we need to check the so-called dispose bit on the previous frame. This flag indicates whether we should clear the previous frame's rectangle back to the background color or keep it around. For this frame, we will not dispose. Now we can move on to frame number 1 and find the area that it'll be drawn to. And since this is not the first frame, we need to consider the blend bit, which specifies whether we pre-clear the current frame's rectangle to the clear color or keep it as is and perform alpha blending. This frame will do alpha blending, so we'll decode the image data and draw it on top. And we display this frame for the given duration. And if you're paying attention, you'll know that before moving on to the next frame, we need to check this frame's dispose bit. And this time, the dispose bit is set. So we need to clear the rectangle back to the clear color. Now we can move on to the final frame. And as usual, we find the draw area. We check the blend bit, but it doesn't really matter here because nothing is underneath. And then we decode the image data and draw it onto the canvas. We wait for the given duration, and we're done. No need to check the dispose bit since this is the last frame. So, we've seen how we can compose or render a full image for each index of an animated WebP. And there are a few libraries out there that implement this logic, and it's typically platform-specific, meaning different libraries for Android versus iOS. And at Instagram, we've been using this FL animated image third-party library. So to clarify, Google provides the official libwebp library, a C library, that handles parsing each frame's metadata and performing the VP8 decoding, but it doesn't handle the actual compositing. And surprisingly, after 13 years, some libraries don't implement the rendering logic correctly. For example, Apple's core graphics stack for iOS and Mac doesn't seem to handle the dispose bit correctly. And you can see how broken some animated WebPs can look in Safari. Now, let's look at a slightly longer animated WebP and walk through a typical decoding flow. When we want to display index 0, we only need to decode frame 0. For index 1, we can hold on to the previously rendered image and then decode frame number 1 and composite it on top, and so on, and so on. And this is what normal sequential playback looks like. But sometimes you need to jump ahead. Maybe we drop some frames and need to catch up, or the player was temporarily hidden from view and now visible, or maybe the user quickly scrubbed forward in time. And when that happens, we need to decode and render everything in between our last cached image and the current target index. But this can take quite a while. For larger WebPs, a single frame can take 15 to 20 milliseconds on an iPhone 15 Pro. With 5 intermediate frames, it's not so bad. But many of our WebPs have hundreds of frames, so render latency can easily become unacceptably slow. The FL animated image library tries to solve this by pre-caching as many frames as possible, but this leads to enormous caches. And often we disable caching altogether, or we limit caching so much that we are still forced to do full decodes most of the time. And as we started recently adding bigger and longer WebPs, as well as more WebPs on the same frame, we knew we needed a better solution. One thing we realized is that we often don't need to decode all of the intermediate frames. For example, in this case, only frames 0 and 3 end up drawing something that remains visible in the final image. So we were able to devise an algorithm to find the minimal intermediate frames that need to be decoded in between some previous index and a target index. And I'll walk you through such an algorithm now. So before we decode anything, we check the intermediate frame's metadata and find the area that each frame draws to, as well as the blend and dispose bits. And using those pieces of information, we'll figure out which frames we need to decode. So we'll start at the end with our target frame number 7. We always need to decode the target frame since it's drawn on top. Now this frame does not have the blend bit enabled, meaning this area will be pre-cleared and thus overwrite anything drawn underneath. So we'll keep track of this in the so-called future opaque area. And then we move backwards to the previous frame. And as you can see, this frame is drawing to an area which will be completely overwritten by the next frame, which means we can skip this frame entirely. And moving on to the next, again, this frame's area will be completely overwritten, so we can skip this frame also. Checking frame 4, however, we can see that a little bit, in fact, will be visible, which means we need to handle this frame. The next question is whether this shape is considered opaque. That is, will it overwrite anything underneath it? On the one hand, the blend bit is set, which means we do not pre-clear this area, and instead we alpha blend it with whatever is underneath. However, the dispose bit is also set, which means that the entire area will be cleared out afterwards. So it's considered opaque for our purposes, and we'll add this shape to the future opaque area. And looking at frame number 3, again, we have a visible portion. So we'll mark this frame as needing to be decoded, and since the blend bit is disabled, we'll add it to the future opaque area. Frame number 2 is hidden, so we can skip. Frame number 1 is also hidden, so we can skip that as well. And frame 0 does have a visible portion, so we'll need to handle that. So we've now eliminated any frames whose draw area would be overwritten by a later frame. And as a further optimization, we'll keep track of the portion that is actually visible for each frame, because with libwebp, you can optionally decode just a rectangular subset of a VP8 image instead of the whole thing, which helps with performance. And we can also filter out any intermediate frames that have the dispose bit set, because the area they draw to will be cleared out afterwards anyway. So we're left with the bare minimum frames and the visible areas that need to be decoded, and we can now proceed with the normal compositing logic. So let's look at this algorithm in practice. Many of our real-life WebPs have hundreds of frames, and users can quickly scrub to the final image. And let's look at how a few renderers would perform in rendering frame 139, the last frame of that chair WebP. For peak memory, FL animated image is abysmal, consuming 397 megabytes just for that one frame, and that's without any caching. Apple's CG image source is much better, clocking in at 10 megabytes, although it's incorrect. And our new renderer is slightly better than that, at 7 megabytes. Now let's look at render latency, where this new algorithm really shines. FL animated image takes a whopping 722 milliseconds. CG image source is not far behind at 636, and this new renderer is only 8 milliseconds. Now let's look at sequential playback performance. In this benchmark, we are burning in 4 animated WebPs to a 720p MP4. This is a common flow when you're uploading a reel. In the transcode flow, caching is disabled, so FL animated image needs to perform a full decode cycle for every frame. The total time for it to render and encode this MP4 is 81 seconds. And with the new WebP renderer, we cache just the previous image, which adds very little memory but dramatically improves the total render time to 4.2 seconds. And WebP playback is much smoother for large-sized cutout WebPs in the Reels editor. You can see it's much smoother on the right, and the corresponding CPU usage is much less. Now let's move on to our last topic, which is WebP with audio. So first, some context. 2 projects at Instagram recently needed audio support during WebP playback. We needed some kind of video format that could support transparent video, or animated images, and audio. The obvious solution to this is to use one of the existing video formats, but it quickly became apparent that none of them were ideal for this use case. Regular H.264 videos don't support alpha. H.265 kind of does, but has patent-related complications. And WebM doesn't have support on iOS, and our audio pipelines don't currently support Vorbis at Meta. Another idea that was floated was to make a custom MP4 file that somehow embeds an alpha mask stream alongside normal, non-transparent video. But this would require very complicated custom players and wouldn't be backwards compatible. Finally, we realized that the easiest approach would be to simply append the audio data to the end of a WebP file. This would enable us to keep our existing infrastructure and ecosystem that revolved around WebP and MP4 audio. And we call this new format Rich WebP. The WebP spec allows for new custom chunks, as long as they follow the basic chunk format. So we devised a new sound chunk that's just a lightweight wrapper for MP4 audio data. These new rich WebP files are fully backwards compatible, meaning all standard WebP players can read and play them, without audio, of course. So to support audio, we created custom players for iOS and Android. The iOS implementation was very straightforward, thanks to some convenient Apple APIs. Essentially, we can build a custom AV composition that includes the MP4 audio data, as well as an empty video track of the desired output size. And then we can define a custom compositor on the AV player to perform our new WebP rendering routine precisely in sync with the audio. And that's it. We plan on open sourcing these libraries soon, so all of you can support animated WebPs in your own apps. And next, I will pass it off to Haisha.
Thanks, Kevin. Good morning, everyone. My name is Haisha. I'm a server engineer in Instagram. Today I'm going to talk about video, and specifically AV1, which is a new open video coding format. We sometimes call it a video codec in short. We'll compare it against some of the other major video formats out there and explain why it is such a compelling choice for us. So much so that we decided to adopt AV1, and in fact we already adopted AV1 as the primary video for streaming at Instagram. And I'm going to convince you that you can also leverage it to improve your video app. There's a very long history of innovation in the field of video encoding technology, dating all the way back 20, 30 years. The most commonly used and widely supported video format today is this H.264 or AVC. It's a pretty old technology. It was created over 20 years ago. And since then, there's many new formats emerged with better efficiency, like H.265 or HEVC, there's VP9, AV1, and so on. In our opinion, AV1 today is undoubtedly the best royalty-free format that you can use. So this is just like very generic statement. What do I mean by efficiency? I don't necessarily mean that we're only comparing the compression or the size of the compressed video files. Naturally, for any encoder, you can configure it to compress video smaller. You can do that by sacrificing visual quality, or you can try to compress it smaller by spending more computation time. There is this interesting three-way trade-off that I try to visualize here between compute and bitrate and visual quality. For every encoder, when you try to compress the video smaller, you also want to maintain a good visual quality, and you want to spend less compute cost. So what I really mean by AV1 being more efficient is that it is offering a better trade-off than some of the other choices. To quantitatively compare AV1 against others, I'm going to quote a graph from a 2021 SPIE paper. It conveniently has this visualized graph to compare some of the major open source encoding implementations, including Intel's SVT AV1. We have the libx264, 265, and Google's libvpx. Here the x-axis represents the computation time, and the y-axis is a compound metric called the BD rate. You can think of it as it represents the compression efficiency, or how well the encoder does the trade-off between bit rate and quality. For an optimal encoder, you want your dot on that graph to be moving to the left and to the bottom. So we can draw two quick conclusions from this graph. Number one is that AV1 definitely has the highest achievable compression efficiency. Compared to VP9 and HEVC, it's about 30% more. Compared to H.264, it's 50 to 60%. And secondly, what we like most about this graph is how wide the red SVT AV1 line spans across the range of x-axes. It makes it a very versatile encoder, and it is good for both offline and real-time use cases. So the graph is still very abstract. Let me try to walk you through two concrete scenarios. Number one, what we call the upper bound, is this question: what is the best visual quality we want to serve to our users? And the answer to that is not the original camera recording quality, because that is an overkill. Usually, camera can record at 4K, 30, 40 megabits per second. What we really need for internet streaming, for social network apps, is just something that is looking virtually perfect to our users. And they're usually using a small mobile phone about 15 centimeters across. And we believe that we can just target 1080p resolution on that screen. Maybe up to 10 megabits per second is good enough. Most of the people will not be able to tell the difference. In this case, if we plot the bit rate and a quality score, and we try to hit that sweet spot, you're going to see that AV1 is going to bring enormous bit rate savings. And this is great news for both our users who may be on a limited data plan, as well as the service, because it cuts down the network traffic cost. The other interesting scenario that we always have to keep in mind is the lower bound. That is, we have to consider users on slow and congested network. As a video service, we have to make sure we have a low bandwidth video representation available to accommodate them. Let's say, for example, we target the minimum required bandwidth to serve video at around 200 kilobits per second. That's a reasonable number. So I'm going to play this. This is from one of the meta engineering blog. As you can see, that H.264 at this bit rate is really struggling. It is producing huge number of blocks, so much so that some of the details on the poster becomes hard to see. But AV1 is still like preserving more details and making the video still watchable at this low bit rate. Okay, so by now, hopefully I convinced you that AV1 is really a good technology. How do we enable it on mobile devices? About 2 years ago, we asked ourselves this question, trying to bring AV1 to Instagram mobile app. And the biggest challenge at that time was really that it was not supported out of the box. Like there wasn't a AV1 decode API on iOS. So what we decided to do to solve this problem is to integrate a AV1 decoder in the app itself. And we chose VideoLAN's open source David decoder library because it is heavily optimized for mobile ARM processor, especially with the big. LITTLE architecture, and offers really good multi-threading performance. And secondly, it's also really compact. When you compile it, you strip it, and apply compression. This library totals about 200 to 250 kilobytes total. And it is performing really well on majority of the devices we tested. There's a caveat that on some of the older devices, it may only be able to do 720p, but for newer devices, you're able to do like 1080p, no problem. You may ask, like, what about the hassle of dealing with the custom integration? There is good news. We're encouraged to see that wider support for AV1 is coming on both Android and iOS. Google just announced earlier this month that Android platform will include a built-in David with an over-the-air update for Android S and above. And we're also very encouraged to see that more devices are getting hardware AV1 decoder. They offer much better power consumption, less heating, things like Google's Pixel, Samsung, and also last year, I think, iPhone 15 Pro and Pro Max with the A17 Pro chip includes the built-in hardware AV1 decoder support. So the future is really bright for AV1. I'm going to pass the mic to my colleague Ryan, who is going to speak about the challenges in deploying the AV1 at scale.
All right, thank you, Haisha. So it's clear at this point that AV1 improves the user experience. However, one of the drawbacks is that it can cost a lot more than the other codecs. The red line on this graph here represents the SVT AV1's performance characteristics. And what you can see here is the x-axis shows the encoding time, or cost. And you can see that it goes very far onto the right. And this x-axis is logarithmic, which means that AV1 can get really expensive. And at our scale, providing this for billions of users where hundreds of millions of videos are uploaded every day, we can't produce AV1 for every video that's uploaded to Instagram. But we can try. And to understand some of the resource optimizations that we've made, let's look at where we spend our resources today. You can break down the compute that we spend today into two high-level buckets. There's this green rectangle, which represents the optional work that we do. When you upload a video to Instagram, we will produce encodings in these premium codecs like AV1, VP9. These improve the user experience, but the app can function without those encodings. And then there's the red rectangle there, which is the mandatory work. And Haisha mentioned H.264. These are basic encodings that are playable everywhere by every device. Without those encodings, we cannot publish a video to Instagram because otherwise not everyone could watch the video. So to produce more AV1, we can reduce how much each bucket costs. For instance, take the green rectangle, for instance. We've made it cheaper over the years by investing in this open source AV1 encoder called SVT AV1. By making this encoder faster in partnership with the open source community, we free up compute. And with that freed up compute, we can produce more AV1. Similarly, for the mandatory work, we can also reduce the cost of those encodings as well. One of the most fruitful recent initiatives is to use special hardware, or ASICs, that produce H.264 encodings, which will essentially free up more compute so that we can produce more AV1. And these machines are more efficient because they're specialized hardware that solves the narrow problem of creating H.264 encodings. They don't need all the overhead of a general purpose computer. So this allows us to produce more AV1, but still this isn't enough. Another tactic that we can use to get more out of our existing machines is to optimize our utilization. So take, for instance, this graph here. This is just for reference. This is our mandatory work, the CPU utilization of our fleet across time over the course of a few days. And what you'll see here is that utilization fluctuates day to day based on user usage patterns. So during the peak times when most of our users are awake, a lot of people are uploading videos to Instagram, and so you'll see that utilization is nearly maxed out. And during off-peak hours, it drops down. But since we have to have enough machines to handle that peak, we don't want that compute to be wasted during the off-peak hours. So there's a lot of idle compute available there. And so what we've done is that we've built a system which essentially allows us to queue up work for these optional workloads. So you can imagine a system where there's a priority queue, and we put these optional AV1 encoding requests in that queue during peak hours, and then the system will get to them during off-peak hours. This works pretty well for AV1 because, as I mentioned, these are optional, and they're not time sensitive, so they will opportunistically upgrade the user experience after the fact. But even after all of these optimizations, this still isn't enough to produce AV1 for every single video uploaded to Instagram because the volume of billions of videos is just too much. So we have to prioritize with our limited compute. And it turns out that prioritization is a very effective strategy because of the distribution of watch time over all videos. So for reference, I have a graph here. If you were to plot all of the videos uploaded to Instagram, sorted by how much watch time they get, you would get a graph that looks like the following. And what you can see, this graph is telling us is that the top most watched videos are watched exponentially more than the bottom videos. So you can think of your favorite celebrities getting millions of views, whereas when you post something to your story, you might get hundreds, maybe dozens of views. So if we can just focus on those videos, if we can just give AV1 to all of those videos, we can give a significant majority of our user base AV1 to watch without spending a majority of the compute. But the question comes, how do we focus on those videos? And over the years, we've developed an approach where we have an ML model, machine learning model, which predicts the watch time of a given video. You can take a look at this figure here. On the left-hand side, those three are essentially the inputs to the ML model. These are things like how much watch time has the video received in the last N minutes. There's characteristics about the person who uploaded the video as well. How many followers is like an important characteristic to know. And maybe things like the video's age. If it's an older video, it might not accrue as much watch time. Now, this machine learning model gives us an output of the predicted watch time in the next 60 minutes of this video. And if that is above a certain threshold, then we will trigger an AV1 request. And the priority queue that I mentioned earlier, the value of that priority queue will be informed by this watch time. So the videos that we predict to be watched the most will have the highest priority and should get AV1 encodings. So this strategy enables us to provide AV1 encodings to billions of users with very limited hardware. We've made a lot of progress over the years in bringing these best-in-class media technologies to Instagram scale. But what's best in class is constantly changing, and we have a lot of exciting work ahead of us. So if any of this sounds interesting to you, consider joining us. I've put the link here. We're hiring, and thank you for having us here. This concludes our talks for today. Thank you.
Thank you so much. We will take a couple of questions from you guys. If you haven't asked a question, feel free to do so. If you go to slido.com and use mdevcamp as a handler, then you can get in, and we would also appreciate it if you would leave us a super quick feedback. Okay, so let's start from the top. What about Instagram HDR support? Sorry, it just clicked away from me, but who's going to take up that question? What about HDR support?
Yeah, I think I read the question was, what about support for Android? And yes, we do support it on Android too. If you have one of the latest devices, one of the latest Pixel or Samsung devices, you can certainly check it out on IG and Threads.
Okay, cool. Moving on. I'm sorry, did you talk about the HDR or the hardware acceleration? The HDR? Okay, so let's take the second one. What about hardware acceleration of AV1?
I'm assuming this is talking about the AV1 encoder because I already talked about the HD hardware decoder. So encoder is something that definitely Meta engineering team is actively looking at, but I can't say more about the timeline. It's obviously going to require new work, and the hardware development cycle is long.
Okay, let's take one more. How do you feel about mobile platforms dragging their feet in implementing hardware AV1 decoding?
I think that's a very interesting question. I do think that we, as some of the major users of AV1 in this industry, have a responsibility to try to evangelize AV1 and get like more people on board. And we really believe that it is a very efficient codec. As specifically for mobile developers, I think for mobile OEMs, they would also see its benefit. And if there is more wide adoption, I think they are going to be motivated to also adopt AV1. But meanwhile, we have like some major, like iOS, iPhone is getting AV1, and we have like Google's in-the-box AV1 decoder. We feel like that will already like play a big role in increasing the adoption.
Okay, let's take a couple more. Let's take it from the top. How does the collaboration between Meta and Videoland works? Do you contribute to the development of the decoder? AV1 can make a real difference at your scale. Who's gonna take that one up? Collaboration between Meta and Videoland.
I can't say I have any like first-person knowledge of this. I do believe that Videoland is open source, and Meta also is contributing to the open source live project. But I do think that we have like close collaboration. This is like hugely beneficial, not just to Meta, but also to the whole industry.
Okay. Is the ASIC hardware open sourced?
Not that I'm aware of.
It's not. Okay, I'm sorry, we are running out of time. You can find all the speakers at the Speakers Corner. So if you go out of the hall, there's a stand labeled Speakers Corner. Thank you, gentlemen, all so much for being here today. Thank you so much. Have a lovely afternoon.